Okay, chapter 10 is all about counting systems. And that sounds kind of weird to think that you're going to sit in a math class, especially a college math class, and you're going to spend a whole chapter learning to count. But it is a little bit more difficult than just 1, 2, 3. What we're going to be learning about is counting the number of objects given certain stipulations, giving certain parameters, giving certain groups of things. And so chapter 10 actually ties back to chapter 2 quite a bit. Chapter 2 was the very first chapter that we started with in 125, and it was all about sets, how we combine sets, how we look at sets, the elements of sets, and all of that kind of stuff. And so we will be using set notation a lot in chapter 10 to indicate our different clubs or our different groups and things like that. And it's going to help us be able to determine the number of items that fall within a certain subset, really, is what we're looking at. So this is good here at the end of the semester because obviously it's been a minute since we talked about sets. It's been a minute since we did anything with them. And so hopefully the chapter 10 stuff will refresh a little bit of the chapter 2 stuff as we get closer and closer to that final. So there is a handout. Like I said, there's not a lot of actual notes. It's going to be learning the process of actually learning how to do these problems. And I have already gone through and I have done all of the homework problems for 10.1, and I think we hit a pretty good consistent amount of examples for how to work these things. So we're going to jump right in and start working some problems. There are different kinds of problems. Some are going to be pretty straightforward, where if there's a one part, that's all we have to be concerned about is just one thing. Others are going to be 2-part tasks or 3-part tasks, and those mean we just have to take more things into account. And we're going to learn how to organize our information so that we can come up with the solutions. So we deal a lot with this club in. It comes out in a lot of different problems in a lot of different formats. So just know that as we move forward. There's nothing special about it. It's very arbitrary. It says, consider that a club in has 5 members: Alan, Bill, Kathy, David, and Evelyn. And we will shorten those to A, B, C, D, E. We have a set. We have a club. It's got 5 members in it. And how many ways can this group select a president, knowing that all members of the group are eligible? So there's a group of 5 people. They need to select a president of their group. Since everybody is eligible, that's the key. There's no other stipulations. There's 5 ways to select a president. Because Alan could be president, Bill could be president, Kathy could be president, David could be president, or Evelyn could be president. Any one of them could be president. So there's 5 different ways we could select a president from this group. 1-part tasks are not typically very interesting problems. There's just not a lot going on. But we will do more with that club and pick presidents and treasurers and secretaries and things like that. Then it gets a little bit more interesting. But the first 2-part task we're going to do it in 3 different methods. Remember that if Pearson asks you for a specific method, then you have to use that method. If it does not, and you really like the list method, use the list method. If you really like the table method, use the table method. And then we will also do a visual tree diagram method. So we're going to do the same problem in 3 different ways, just to show you different ways you can approach all of these problems. It says determine the number of 2-digit numbers that can be written using only the digits 1, 2, and 3. I know Pearson gives you a couple homework problems like this in the table method, and they have you finish filling it out. And so we'll start with the table method. The table method is where we're going to make a table noting that we need a 2-digit number. So I'm going to put the first digit over along the left like this, just indicating that. And I'm going to put my second digit across the top. This is how we would lay out our table. Our digits can be 1, 2, or 3. So I'm going to put 1, 2, and 3. Same across my top. 1, 2, and 3. This is how we would set up our table. And then the way that it gets filled in is we look at the intersections. My first digit along this first row is a 1. So when it intersects with the second digit that's a 1, I'm making the number 11. Slide over. My first digit is still 1, but now my second digit is 12, or 2. Same thing for 13, the last one. So across my row, all the first digits are the same. Down my columns, all the second digits are the same. So when I go to my second row, it's going to be a 2 in the first digit spot, but it's still a 1 in my second spot. So I made the number 21. Slide over, I do 22. Slide over, I do 23. Last one will be 30s. I'll have 31, 32, and 33. On Pearson, they don't make you start from scratch. They set up the table for you, and they even usually fill in most of the table and leave 3 to 5 of them empty, and you just continue to fill it out. But you can use this even on problems where they don't give you a table, if you so choose. It can be helpful, especially with the dice problems. A table is going to be really helpful because there's kind of a standard table that comes out of the dice problems that you'll see here in a minute that can be really helpful to have on hand. The list method is really kind of what I think is the more common. Like if you were just sitting down trying to do these, I think this is a way you would approach these problems because it's the way that seems most logical. We know that we have the digits 1, 2, and 3. So using the list method means we literally list out all the numbers. What are the possibilities? Well, I'm going to be very methodical so I don't accidentally forget one. And I'm going to start with 1 as my first number. And I'm going to do every possibility that I can with that number first, and then I'll move on to a different starting number. So 1 can go with 1. 1 can go with 2. 1 can go with 3. There's no other numbers for me to pair 1 with, so I would be done with 1 in the first position. Then I would go to 2, and I would do 2 with everything. Notice I'm getting the same numbers, and even with the way that I'm organizing it, I'm really doing the table method. So it's really your choice. The risk with the list is that you could accidentally, like if you had a larger number of digits or more possibilities, you could accidentally forget one somewhere along the way. And so the table kind of helps you keep it more organized so that obviously if you have an empty box, you know you need to fill that in. Whereas with the list, you may get so many numbers or so many different options going that you don't really notice that there's something missing. But notice from either of these, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different possibilities. Or 9 different ways that we can make a 2-digit number using just the digits 1, 2, and 3. So it doesn't matter which method you use. It still works. And then we're going to look at the visual method or the tree diagram method. When you see tree diagram, you can think like a factor tree almost of sorts. Except that we're going to start at the top with like our first digit. And then we have a second digit. That's what our tree is going to be composed of because we're only thinking about 2 different digits. And then at the first digit, we list all of our possibilities. Well, we could have number 1 as our first digit, number 2 as our first digit, or number 3 from our first digit. These are all very separate from each other. They're going to be their own trees of sorts. But if 1 is my first digit, well, 1 could be my second digit, or 2 could be my second digit, or 3 could be my second digit. The first digit in this problem does not change what selections we have for our second digit. There's still 3 options if 1 is the starting option. If 2 is our starting digit, we still have the options of 1, 2, or 3 being our second digit. Same thing for 3. And from this visual, we could come up with the same numbers we have in our table or in our list. Because if one's our first and one's our second, we have the number 11, then 12, then 13, so on and so forth. Notice if 1 is our starting digit, we have 3 possibilities. If 2 is our starting, we have 3 possibilities. If 3 is our starting, we still have 3 possibilities for a total of 9 possibilities. That's what we found up here using the list method. That's what we found using the table method. You are always going to have the same amount of possibilities regardless of which method you choose to use. The answers aren't changing, just your way of approaching them. So all 3 of these could be used. Obviously, we did the same problem 3 different ways. You're not going to be asked to do that. Most of the time you are given a problem like determine the number of 2-digit numbers you can write using only the digits 1, 2, and 3, and they don't give you a method to use. So you can use any of these if you so choose. All they're going to say is there are blank numbers of ways, and you put in the number of ways. In this way, it would be 9. Are there questions about table, list, or visual before we move on? So if I work one way in the notes, just know that you could use any of the other methods as well. All right, let's flip over. We're going to do a dice problem. I will tell you a table seems to be the easiest way for me with the dice. It says determine the number of different possible results when rolling 2 ordinary dice. So we got 2 dice. I should have grabbed some from somewhere. That would have been helpful to visualize, but the way that it's easiest to kind of differentiate the dice instead of calling them like dice 1, dice 2 is really to change the color of the dice. So I'm going to have a green dice and a blue dice, and we're going to determine what's going to happen with these. So think about a standard dice. Standard dice has 1, 2, 3, 4, 5, 6 sides and that many dots. And so those are the possibilities that can happen on a single dice. And if we roll 2 dice, then we can have those possibilities show up on both dice. So I'm going to do a table. I'll put my green dice across the top. In your book, they do green and red dice. Again, the color is totally arbitrary. That's more to be helpful on identifying what's going on. Those are my possible outcomes with my green dice. I could roll a 1, a 2, a 3, a 4, a 5, or a 6. Then I'll put my blue dice over here. Again, if you want to call them dice 1, dice 2, totally fine. There's nothing wrong with that. So with my blue dice, again, I can roll a 1. I can roll a 2. A 3, a 4, a 5, or a 6. Those are semi-straight lines. Not too bad. And then the table ends up getting filled up pretty much the same way we filled up our table on our 2-digit numbers. If I roll a 1 with my blue dice and I go over, I could roll a 1 with my green dice. So I make it kind of look like an ordered pair where I rolled a 1 and then I rolled a 1. Then I move over. If I roll a 1 with my blue dice, I can roll a 2 with my green dice. I can roll a 1, I can roll a 3. So on and so forth until I fill up my table. You may be asking, why would you want to fill it up? Can't you just count the number of squares? You can, but sometimes they're going to ask you for you to fill it up. They're going to give you an empty table or a partially empty table and have you fill it up. There's also a lot of problems that deal with these dice where if you have a filled-in table to reference, it makes your life a lot easier. Because they will ask you, how many different ways can you roll 2 dice with a sum of 5 from the 2 dice. And if you have this table filled up, then you just go and look and say, well, if I roll a 2 and a 3, that totals 5. If I roll a 4 and a 1, that totals 5, and so on and so forth. And you can kind of find out where those are in your table. And it makes your life a little bit easier instead of having to make the table over and over and over again. 3, 1, 4, 1, 5, 1, 6, 1. Notice we have 6 rows, we have 6 columns. 6 times 6 means there's 36 ways, or 36 different possible outcomes when we roll the dice. In your homework, they'll ask you questions like, how many different ways is there to roll 2 dice whose sum lie between 2 and 10? That was one that I saw. If they say if there's a sum that lies between 2 and 10, you don't include the dice that total up to 2 or anything that total 10 or greater. You want the ones that total in between those 2 numbers. So be careful, because if not, you'll count and do all this work and then realize that you accidentally left one in. Because I know on that problem specifically, I left in the 0.11 because that totaled 2, and then I'm like, wait a second, that's my ending point, and I don't want to include that. So tables can be nice. They can keep things organized so you don't accidentally leave out one of the rolls of your dice and things like that. Any questions on using the table? All right, let's go back to our club N that has 5 members. So same club, same members, A, B, C, D, E. Now we're going to find the number of ways that the club can elect both a president and a secretary. We can assume that all members are eligible, but no one can hold both of the offices. So if A is the president, A can't also be the secretary. That's what's going to end up happening. So your book does this with a table. I'm going to do it with a list method, and then I'll show you the table. And that way you can see it in 2 different ways. So I'm going to assume that A is president, because I'm going to start my list. If A is president, I can't go AA as my first pairing, because A cannot be president and secretary at the same time. But if A is president, B could be secretary. If A is president, C could be secretary. If A is president, D can be secretary. If A is president, E could be secretary. Just going down the list. I'm done now if A is president. Now I'm going to do the exact same process for if B is president. If B is president, A could be secretary. If B is president, C could be secretary. You'll kind of see that there's a little bit of a pattern that happens. If C is president, A could be secretary. C could go with, not with C again, but it could go with B. C could go with D. C could go with E. D could go with A. D could go with B. D could go with C. D can't go with D, but D could go with E. So notice what we're really doing is we're making sure everybody's paired up, both being first and being second, with everybody else. E could go with A, E could go with B, E could go with C, and E could go with D, but E can't go with E. I have 5 rows with 4 in each. So that gives me 20 possible ways of selecting both a president and a secretary from the group when everybody's eligible and no one can hold both offices. And that was just the listing method. I just paired everybody up. You could have also chosen to do a table like we did with the green dice and the blue dice. Table works pretty much the same way, only you'll notice we have a diagonal of empty spaces. But those empty spaces correspond to when you would be paired up doing both the presidential job and the secretarial job at the same time. And that's why they're empty. And we just ignored those when we made our list. And so we didn't include those and we wrote everybody else out. Still get 20 results. Both works. You could do a like a tree if you wanted to, where you list A across the top, B, C, D, E, and you would have all those branches coming down. You just wouldn't have A connecting to A and things like that. And you'd still get 20 methods or 20 ways. Clarifications, questions? All right, let's put another stipulation. Now find the number of ways that Club N can appoint a committee of 2 members to represent them in an association conference. So, up here, when I made my list, notice that I had AB and I had BA, because the order mattered very much. The first one indicated the presidential spot, the second one was the secretary spot. And so the order of my letters or the order of my members mattered in this case. Down here, I'm just doing a 2-member committee. So both of my committee members are on equal ground. So the order of my letters, the order of my committee members does not matter. So if I write down AB, that's the same thing as BA. And so I won't need to write BA again. So I'm going to pair up all of my A's first, because A could be in the committee with B, A could be in the committee with C, or with D, or with E. And then I go to B's. B could be in the committee with A, but I already wrote that down, so I'm not going to write it again. So B could be in a committee with C, or D, or E. Same thing with C. I've already written C with A and C with B. So C could be in a committee with D, or C could be in a committee with E. And then D could be in a committee with E. Notice that our list is a whole lot smaller this time. And that's because the order matters. We had 4 here, 3 here, 2 here, and 1 here, for a grand total of 10 ways to make a committee of 2 members. So we have to make sure we pay attention to, if we're making a committee or a subgroup or things like that, oftentimes, almost always unless they tell you, the ordering of our letters or of our group members will not matter at all. When it comes to president and secretary and all of that kind of stuff, that does matter because they're holding different positions. It's not equal playing ground. So there's actually less ways to make a subgroup or a committee of 2 members than it is for this group to select a president and a secretary. Questions on any of this? We're going to do some tree diagrams next. Because really we've done a lot of listing, a lot of tables outside of the original problem to show you what a tree or visual diagram looks like. We haven't done any. So we're going to do those on the next ones. We're going to use tree diagrams to find the number of 3-digit numbers that can be written using only the digits 1, 2, and 3, assuming that you are allowed repeated digits. That means you could have the number 1, 1, 1. You can have the same number in all 3 spots. And so what we're going to do is we're going to make tree diagrams to find out all these numbers. I will warn you, I am not very good at making these evenly spaced. So I'm going to cheat a little bit because I can't. I'm going to show you the diagram the book uses. Because they can evenly space. Man, I've tried evenly spacing these, and by the end, I always get to where all my lines are starting to cross, and it's not as pretty. I'm just not good at spatially spacing them, I guess. So my first digit can be a 1, it can be a 2, or it can be a 3. The book does a lot of their tree diagrams going horizontally. It's really your preference on if you have room to go horizontally or if you need to go vertically. And honestly, there's no reason why you can't do your trees completely separate. In terms of maybe you need to just look at the tree where the first digit's a 1 and complete that tree, and then go down on your paper and do the tree where 2 is your first digit and where 3 is your first digit. That's what I had to do in the homework, to be 100% honest, whenever I was doing it, because my trees got a little crazy. I'll just show you. So I did a tree here, and that's just if the first switch is off, and I did that, and then I went down and did the exact same tree over here if the first switch is on, because I didn't have enough space, and that's how I had to spatially do it. It's totally okay if you have to do that. But the book is able to do it because it's all typed out. So the second digit, no matter if your first digit's 1, 2, or 3, can be 1, 2, or 3, because we are allowed repeated digits. And so from each of my first digits, I'm going to have 3 branches off. And because we're allowed repeated digits, from each of my second digits, I'm allowed 3 branches off. Because if I have the number 1, 1, the next digit could be a 1, a 2, or a 3. See how small they get? They get really small. But with a computer, you can make it all nice and evenly spaced. And then the way you would read this in order to actually come up with your numbers, if they were to make you list them out anywhere, you start with your first digit. That's a 1, 1, 1. So that would be the number 111. Then you'd have 1, 1, 2, 112. 1, 1, 3, that's 113. So then you're kind of done with this branch of your tree. Then you'd go to 121, 122, 123. And you would list them all out. At least the homework problems I encountered, they did not make you do this. In terms of listing out all the individual ones, they would ask you how many possibilities or how many different ways could you do it. But I will say having them listed out is helpful, because maybe they put a stipulation on this problem. Right now it's totally free. You can have repeating digits. But maybe you can have repeating digits, but your last digit can't be a 3. And so then you can go through and you can mark out all the ones whose last digit are 3, or whatever it is that they may tell you. So the trees are nice, but if you're not good at spatially arranging them, then they can get clustered really fast. But again, you can look at each tree separately. You could look at the first digit as its own tree with a digit of 1, the first digit as a digit of 2 as its own, and then move down and look at that one all by itself and it's going to take up space. I'm not saying it's not. But you might be able to keep it a little less hectic. Any questions on how we set this up? These are problems you very well could choose to do lists for if you wanted to. This one, I've specifically set aside a couple problems here at the end to show you how to use the tree diagram. Again, because by listing, you do run the risk of accidentally leaving something out. If you do the trees, then you can see where you need to fill in your branches, and you can see where your conclusions are coming from at the end of your trees. So it's just an organizational tool, really, more than anything. But you could always use lists. I don't know if you could use a table, really, for this one, because you have 3 different things going on, and our tables really only have 2 sides. So I don't know a good way to use a table. All right, let's look at part B. Part B, obviously, I didn't leave as much space, so you know the trees are going to be a bit smaller. It says repeated digits are not allowed. That means if your first digit's a 1, nowhere else in that number can be the number 1. So you can't have number 111. You can't have number 121 or 131 or any of that. So that limits and makes our trees quite a bit smaller, because if our first digit is a 1, our second digit can only be a 2 or a 3. That's it. It can't be a 1. So we're only going to have 2 branches off of each of our first digits. Because if you're a 2, then you can only be a 1 or a 3. And if you're a 3, you can only be a 1 or a 2. So there's less branches that happen. And then from there, because no repeated digits are allowed, if I have a first digit of 1 and a second digit of 2, that forces my third digit to be a 3. There's only one option. If my first digit's a 1 and my second digit's a 3, that forces my third digit to be a 2. So there's a lot less options that happen because I cannot repeat. And thus I have a much smaller tree that I could actually make without getting too clustered. And instead of having 27 different possibilities for these 3-digit numbers, I only have 6. There's only 6 possible ways that I can combine the digits 1, 2, and 3 without repeating them to give me unique answers. And in your homework, it looks like we only have 2-digit numbers that we end up playing around with. All right, let's flip over. I think we're flipping. We've got one more problem on the back. There's a couple of different, there's 2 notes at the top. Replacement means you can have repetition. Whoa, that's not fully up there. Replacement means you can have repetition. Without replacement means you can't have repetition. So sometimes, like the last problem, it'll tell you have no repeating numbers. Other times it'll tell you that you're looking at items with replacement or without replacement. You could be drawing balls out of a bag, and if you draw a blue ball, you put the blue ball back in the bag. Obviously, you have another option of drawing that same blue ball back out. That's with replacement. You can have repetition. Without replacement means there's no repetition. If I draw a blue ball out of the bag, I don't put it back in. It's no longer available for me to draw. That kind of stuff. And your very last homework problem is a paneling problem, is a switch problem like this one. This one states that Pamela's computer printer allows for optional settings with a panel of 4 on-off switches. Okay, so each switch has 2 different settings. You're either on or you're off. That's what that is. How many different settings can she select if no 2 adjacent switches can both be off? Okay, so if they're side by side to each other, they cannot be off-off. There's got to be an on somewhere in between them. You can have on-on, but we can't have off-off. That's what that says. And so they chose to use a tree. I chose to use a tree as well for the homework one, and I'll show you. They did theirs horizontally. I left the whole page here, so I'm going to do it vertically because I think that's a little bit easier. So for our first switch, we have 2 options. We can be on or we can be off. So both of those start with O's, so that doesn't really help. So I'm going to call off a 0 and on a 1. You could make them stars and hearts. It really does not matter what you want to call them. You could even write out the words if you wanted to. It just gets more clustered. So I'm going to call off with a 0, on with a 1. So we can have the option to be off or we can have the option to be on. Now, for my second switch, I guess I should make these numbers. This is switch 1. Then we will have switch 2. Switch 2, I can't have off-off, right? I can't have 2 that can be off-off, so I only have one option going from the off one. I have to be on for my next one, because I can't have 2 back-to-back that are off. Does that make sense? It cuts my tree a little bit. If I'm on with my first switch, I can be either off or on. It does not matter. Because I can have on, I can't have off. So let's look at switch 3. For switch 3, from this one, I'm going to go from an on. So if I'm going from an on, I can go to an off or an on. What about over here with on, off, what can I go to? I have to go to an on. That's right, I can't go to an off. So I only have one branch. But over here, I can go to an off, or I can go to an on. All right, we only have 4 switches, so I just have to go one more branch. I can go to switch 4. Again, if I'm going from an off, I only have one option. I have to go to an on. If I'm going from an on, I can go to an off or an on. If I'm going from an on, I can go to an off or an on. If I'm going from an off, I have to go to an on. So Pamela's computer printer could have her switches being off, on, off, on, or off, on, off, off, on. That's all the options from this branch where we start with an off. Sorry, you can't see all that. If I start with an on, I could go off, on, off, or I could go on, off, on. So I've dealt with this whole left branch of my on. I could be on, off, on. It could be on, off, or I could have all ons. So I had 1, 2, 3, 4, 5, 6, 7, 8 ways. Now, do you necessarily have to list them out like this? No, because look, we have 1, 2, 3, 4, 5, 6, 7, 8 ending branches. So there's 8 ways that we could have done this. So as you're filling out your branches, you don't always have to go off onto all 3 or 2 options. You pay attention to what the limiters are, and since I couldn't have an off, I didn't make those branches. That way I didn't have to worry about them. Are there any questions or clarifications?